What's up, scholars? So we are continuing our unit here on work, energy, and power. Today we're going to do at least two examples of conservation of mechanical energy. What's great about this is we're going to be solving some similar problems to how we did before, similar problems to what we did before, but we're going to be doing them in what I think is an easier way. So the biggest concept that we have to start with is that mechanical energy is always conserved. Let's remind ourselves mechanical energy. I'll pause and write out the definition. So mechanical energy is just the sum of the kinetic and potential energies of an object, and it's conserved in closed systems. So put simply, the amount of mechanical energy that you start with at the beginning, so ME naught, is equal to the final mechanical energy that we have. And as we've showed before, that just breaks into the components, kinetic initial and potential initial. Whatever that sum is, it's going to be equal at the end to the sum of the final kinetic plus the final potential. And we saw this a little bit in the FET skate park where we were looking at the energy pi. So let's look at that next. So let's say that we've got a roller coaster that works in kind of an unusual way. Instead of it having that hill that goes to get to the top, let's just pretend like there's a motor that lifts the car that people sit on straight up to the top. Okay, so there's a motor and it's going to do some positive work. So let's call that the work done by the motor to lift it from here to here. And so once it's done its work, we've got our cart here, and let's say that the initial velocity of the cart is 0 meters per second. Now we're going to assume for easiness here that there's no non-conservative forces. So what we mean by that is there's no air resistance, no friction. So I'm going to put no non-conservative forces. So that means that there's no air resistance or friction or anything like that. Now, what we mean is that this is a closed system. As this moves down, the only thing that's going to act on it is gravity, and that force is a conservative force. What we mean by that is the amount of work done right here. So remember, work is force times distance in the direction that you move it. Now we're moving this, let's say it takes us infinitely long to do this. Let's say that this motor is applying essentially exactly the weight of this box and lifting it up to the top. So the force that it would apply, the work done by the motor, would just be the weight of that times the distance. Let's say it moved at a distance, I don't know, h, height h. So our work becomes mg times the distance, h. That should look familiar. The work done here, work done by the motor, is exactly equal to the gravitational potential energy, or we'll just shorten it to PE, that it has right at the top. And that's going to be mg, and let's call that h naught, since that's going to be the initial position up here. So what's cool about this is if we plugged those numbers in, we would know exactly how much energy we have to work with. So let's do that. So I've just made up some numbers just so that we have something to work with. 1,000 kilograms, let's say that the car at the top of this roller coaster and the people is 1,000 kilograms. Let's just, for sake of easiness here, call g around 10, and let's say the initial height is 30 meters, or about 100 feet. Okay? So if we were to plug all that information in, we would know that the amount of potential energy that we have to start with would be just these numbers plugged in. I'm going to do that now. So I've plugged everything in. We get 300,000 joules. Now, what's kind of interesting is, in a bunch of ways, which we may get to, energy is kind of just made up. It's a way that we account for who has sort of currency to do stuff. And when I say who, I don't mean people, I mean objects. So if you have energy, that means that you can do stuff. In this case, work was done to this box, so it can do things like move down the ramp and actually move back up the ramp, because it will still have some kinetic energy in different places. Now, the important thing is we don't really care how much energy we have. What we care is what forms it's in. In this case, it's just going to convert between some combination of kinetic and potential at the end. We know, because this isn't moving, that there's no initial kinetic energy. And so what we're going to do is we're going to account for how much energy is in which type of form by using an energy pi. And I'm just going to, for fun here, let's say that potential energy, remember we're talking strictly gravitational potential right now, we're going to say that that's colored in green, and I'm hoping I can be consistent here. Let's say that kinetic energy is going to be colored in blue. If you've got pens at home or colors, join me here. So at the beginning, we know that the energy pi should be 100% colored in terms of all, I'm going to darken that in P. Hopefully you can see that. So there are some basic questions that we can ask, and I'm going to modify my drawing here just a little bit so it's more clear what's going on. So we're saying here that we've got a roller coaster has a big hill at the top, which you'll always see with roller coasters. They need the biggest hill at the top because that's where we give it all the energy. Next, we've got sort of this intermediate dip. It goes down quite a ways. I'll fill this in a little bit. It doesn't go all the way down. So let's call this, up here we can call this position 1, and we can draw our pi. Let's call this position 2. We can draw our pi. Position 3, we're kind of halfway or part of the way back up. And then position 4, let's say that we've made it all the way down to the ground. So one of the sort of interesting questions we can ask that's, I think, fairly intuitive is what's sort of the balance of energy? And we're going to do this very roughly speaking. And then I'm going to show you the utility here where we can either calculate heights or speeds. So pause for just a moment and see if you can fill in, roughly speaking, and just go for rough here, what each of those energy pi's looks like. I've already given you the answer to position 1. Give it a try. Let's check our work. So remember we had 300,000 joules to start with, which just means that the size of our pi is never going to change. So we start with all potential because we're not moving. Then we get to sort of near the bottom, and so because we're not all the way down to the bottom, what's important to note is that we still have some potential energy left. Now, I didn't mention something that we did here, but what are we comparing the height to in terms of potential energy? So I should mention that we're kind of considering the ground here to be 0. We call this our reference height. What we mean is that when we measure MGH, we're measuring where this height equals 0, and up apparently to here is 30 meters. So later on we'll give us some numbers for what that height is, but we're comparing how much potential energy we have to this reference height here, which is part of why I'm saying it's all made up, because it depends on where you pick your height to be. Okay, the cart's moving down, it gets back up near to the top here, and we're mostly potential. It's moving slower with a little bit of kinetic left, and then finally we get to the bottom. I didn't draw very well, but let's assume we're all the way at the bottom. It would be all 100% kinetic energy. All 300,000 joules of energy here is converted into kinetic by the end. So I wanted to just quickly show you this before we actually go solve some problems down in this PhET simulation. So a couple of things. First, notice we've got our energy pie chart here. Let's just pretend like that's 300,000 joules. Same idea though. Now what's interesting about this is once I actually hit the play button, you're going to see this potential. I conveniently mixed the colors up, that's okay. You're going to see this potential be converted into kinetic and back and forth seemingly forever. So you can see there, being converted back and forth between the two. Excellent. Now, a couple of things I want to point out to you. So we're going to restart the skater. And I mentioned that we have a reference height. What's kind of cool in this simulation is they'll let you turn that on. And watch this, by just simply changing where my reference height is, I can make the energy that the skater has change. So if I say, okay, halfway up the ramp, that's actually where 0 is. Then the total height that they have relative to that has gone down. So what we can do is be really clever and smart about what we say is height equal to 0, and it can actually make our lives easier. We'll show you that here in just a little bit. And the last thing I kind of wanted to tease here is in this simulation so far, because it says friction is equal to none, we're assuming there are no non-conservative forces. So friction isn't there, air resistance isn't there. But watch what happens right away. The total stash of energy we have, 300,000 joules in our problem, can only be converted between potential kinetic right now. Once I turn on a little bit of friction, watch what happens to my overall amount of energy that I have. So the overall energy pi is still, 300,000 joules or whatever, but notice I have less to work with, which means I'm not going to go as high, I'm not going to go as fast, and eventually I'll turn the friction up to simulate this so it'll go faster. Eventually, things like this, even though they started with a whole bunch of energy, will stop moving, they'll stop climbing, things become very uninteresting, and that's because of thermal energy. So now what I'd like to do is get into the actual usefulness of energy conservation. Not that drawing these pies isn't a lot of fun. What we want to be able to do is, specifically in this case, we want to be able to tell our passengers on this roller coaster how fast they're going to be going at these different locations. And this actually becomes really easy. We don't need to know any information about the length of the track or anything like that. All we need to know is the initial height and the final height. I'm going to show you how we can do that right now. So we've got three heights, and what we want to be able to do is to come up with a formula that will just spit out how fast are we going there, and it's actually surprisingly easy. Anytime you have a conservation of energy question, you're going to start with this basic fact: the energy is conserved, the initial mechanical equals the final mechanical, and remember those break down into kinetic and potential, both initial and final quantities. Now, we're going to try to keep this generic and then plug in values as we go, but we do know that at the beginning, the kinetic energy is 0. So that's going to make life easy for us. That's 0. And then we do have a place where there's going to be no potential energy at the end, but let's leave that in for right now. So let's expand this out. We want the mgh0. That's going to be the potential energy right here. And we actually already know the answer. The answer is going to be 300,000 joules. Now, we're not actually going to calculate that. It's going to end up not being necessary to know the number of joules, because remember, energy is made up. It's just for accounting purposes. The kinetic energy final is going to be 1/2 mv final squared. And what I mean by that is, what is it going to be at position 2, and then later we can calculate it at position 3 and position 4. That's what kind of we're after here. We're going to solve for that in just a moment. And then finally, the PE final is going to be mgh final. The final potential energy is going to just depend on the height that we look at, height 1, height 2, height 3, or height 4. So what's beautiful about this is that we can do some canceling, and that's actually why we don't want to use energy in a lot of cases. So if you notice, there's a mass in each term. We're going to go ahead and cancel that, and then our goal is to get VF by itself. Remember, we want to know the speed at each position on the roller coaster. So in order to do that, let's try to get all of the other information over to here. So I'm going to subtract the GH final to the other side. So I'll have GH0 minus GH final, and that equals 1/2 V final squared. Let's do a little bit of factoring, and then I'm going to multiply both sides by 2. So 2 times G, and then in parentheses we have H0 minus H final. Do extra steps if you need to get to where I'm at there. That equals V final squared. So I'm going to take the square root of both sides and then flip it around. So V final is going to equal the square root of 2G times just the difference in the heights. So H0 minus H final. So this isn't an equation that we necessarily want to box in and memorize. The equation that we need to remember is just this simple fact: energy is conserved. We've got this equation, and what I'm going to do is on note cards here, we'll do each calculation. So I've plugged it in for position 1. That was at the top. It's kind of a naive calculation, but I want to see what this equation can do for me. So position 1 was at the top. I was at 30 meters. That's where we actually started. So if you notice, I plugged in 30 minus 30 for our initial minus our final, which means that term is 0. So 0, it doesn't matter. That's 0. This makes sense. The final velocity when we started was the same as when we started, which is 0. Seeing that example, take a moment, see if you can calculate the speed at each position, and then I'll show you all of the results at the end here. Okay, so for position number 2, which was at 10 meters off the ground, we plug everything in. 2 times G times the difference in the heights. And when you punch all that in, you end up with 20 meters per second. But I wanted to show you how we can be a little bit smarter than that. So check this out. If we pick a smart reference height, so we just briefly look here and we recognize that we need to just know the difference between these heights, figure out how much speed it's picked up as it has fallen. That's really what this equation is saying. It's 2 times g times the difference in the heights. So what we could do is temporarily, because energy is made up, say that this height is actually 0. And it can't go any farther than that. That kind of makes our energy pi obsolete, but in fact it makes our calculation a little bit quicker. So we just do, instead of the difference in the heights, just 2gh, which is 20. We still end up with 20 meters per second as our final height when we pick a smart reference height. Not much to say about position 3. Very, very similar. You can take the difference and plug it in. The difference is 10 here between 30 and 20. Or you can go with the smart reference. So we know that this h just ends up being the difference, and we get the same results. So not much to say about position number 4, 30 minus 0. So we started at 30, end at 0. Here, it's kind of indistinguishable from the smart way to do it, because we already made our reference 0 right here. So there you have it. We were able to calculate the speed at any of these locations. And notice that even though, I don't know how interesting it was, but even though we were able to calculate the total amount of joules, that's not actually the useful part. The useful part is being able to predict the speeds of things, and the beautiful thing is we didn't need to know the length of the track or anything like that. All we needed to know was its position.